Good afternoon. If you have any questions, I can answer while your friends are joining meeting. I'll wait for another couple of minutes and then I'll start if you don't have any queries.
Sir,
Yeah,
so like in this head loss term, this Q dot in, like while deriving this head loss from first law of thermodynamics, we did not use that, like it is not intentionally added. Like that heat.
sorry, I couldn't hear you. Can you repeat it again?
So like while deriving this head loss term from first law of thermodynamics,
Right.
so like we did not use like this Q dot in is we are adding intentionally or not. But like you told that it is not intentionally added. It is due to internal friction like.
Right. Heat may be generated by internal friction. Yeah.
Yes,
See,
yes.
what will happen is the uh, internal fluid friction between layers of fluid which are gliding over each other, that will lead to a conversion of mechanical energy to internal energy. So when the internal energy increases, the temperature will rise, and then
Yes, sir.
there may be some heat transfer because of that.
Okay, if we add intentionally some heat, then that will not be included in this head loss term.
No, that will not be included. That has to be there separate.
Okay,
Yes.
okay, okay.
You have to have a separate budget. But we'll be applying this equation to the turbines and pumps where we are not going to add any heat in future. Okay.
Okay, okay.
All right. To make my point more clear, I'll look at review streamlines and stream tubes, and then I'll come back to this again. All right. Is the screen visible to you?
Yes, sir.
Okay, thank you. So we need to review a bit of fluid mechanics. Well, we'll review only the portions that are required for this course. Okay. So let us quickly look at streamlines, stream surfaces, stream tubes, and stream filaments. Now, a streamline is a curve in space that is everywhere tangent to the velocity vector. And as you might have read in your second year, you can write the equation of a streamline in this form: dr cross v equal to the zero vector. So here r is the position vector of a point on the streamline, and the displacement vector dr will be tangent to the streamline. And if the curve is a streamline, then the displacement vector dr will be parallel to the velocity vector, in which case the cross product is 0. So you might have seen it in this form in your whatever book you might have referred to in your second year. Now, if you look at the components, suppose I say V has components Vx, Vy, and Vz with reference to a coordinate system, Cartesian coordinate system XYZ. Okay, and Here I've used the notation E subscript x, E subscript y, and E subscript z for the velocity, for the unit vectors in the x, y, and z directions. Some other authors might have used I, j, and k here, but I have preferred to use this. So dr will be dx ex plus dy ey plus dz ez. So this vector equation which I've written on top is equivalent to 3 scalar equations. Okay, and you might have seen the equation of the streamline in component form as dx by the x component of velocity vx equal to dy by the y component of velocity vy, and that is equal to dz by the z component of velocity. Now each of this is also equal to ds by v, where ds is the arc length along the streamline and v, capital V, is the magnitude of the velocity. So perhaps you might not have seen the fourth equality here, but I'm adding it here for the sake of completeness. So the arc length, you know, is the square root of dx squared plus dy squared plus dz squared. And the magnitude of the velocity is square root of vx squared plus vy squared plus vz squared. Now, if you look at the parametric equation of the streamline for a 3-dimensional flow, I can write it in the form the position vector r, that is the position of vector r, is the position of a point on the streamline, is a function of the arc length coordinate s. Okay. So equivalently, we can say the x, y, and z coordinates are functions of this parameter s, which is the arc length. So here, the vector r denotes the position vector of a point on the streamline, and s is arc length from some reference point along the same streamline. So the vector form of the equation one can write as dr ds is equal to the velocity vector by its magnitude. Now, if you divide the velocity vector by its magnitude, what you get is the unit vector in the direction of the velocity vector. And dr ds is also a vector which is tangent to the curve defined by the equation r equal to rs, and it has unit magnitude. So if this curve, arbitrary curve, is a streamline, then you have dr ds equal to v by v. So this again is a vector equation which will have 3 components, which you can write in this form. Dx ds is vx by v, dy ds equal to vy by v, and dz ds equal to vz by the magnitude of the velocity. So you have 3 scalar equations, which may be coupled equations, of course, for the x, y, and z components of a point on the streamline. Now, in many cases, we will be dealing with 2-dimensional flows, so we will not be interested in the z component. So z is a constant in that case. So here we will have just x and y being functions of s, and you have 2 equations, dx dx equal to the x component of velocity by v. And when you look at the dds of the y coordinate, it is the y component of velocity by the magnitude. Now, if I take this second equation and divide it by the first equation, then the ds and the capital V will cancel out, and you simply get dy dx equal to vy by vx. So the slope of the curve in the xy plane, if the curve is a streamline, is equal to the ratio of the y component of velocity to the x component of velocity. And these can be functions of x, y, and t for a 2-dimensional flow. If it's steady, it will not depend on time, the velocity components, but if it's unsteady, it will depend on the time as well as the 2 spatial coordinates. So since the flow is 2-dimensional, there is no z dependency. Now, let me ask you a question. We'll need this concept in this course. Can 2 streamlines in a flow field intersect at a point?
No, sir.
No, sir.
No, sir.
So what is the reason why?
It can't have 2 different velocities at the same point.
Okay.
It cannot have 2 tangents at the same point.
Okay, so if suppose the velocity vector is non-zero, and if they intersect, then there will be 2 tangents, right? But in your second year course, you must have come across this term stagnation point. So do you recall what is a stagnation point?
Yes,
It is
sir.
a pop.
Yes, sir.
Yeah.
Yes.
A stagnation point is a point in the flow field where the velocity vector is the zero vector or the null vector. So it is a point where all components of the fluid velocity are zero. Now suppose I have a coordinate stagnation point with coordinates x subscript s, y subscript s, and z subscript s. So I'm putting this subscript s to denote the stagnation point. Then by definition, the velocity vector at this point will be zero for all instants of time. Of course, if the flow is steady, there will be no time dependence, but even if it's unsteady, at each instant of time, it will be zero. So this again is a vector equation. It is equivalent to three scalar equations. That is, the x, y, and z components of the velocity at this point must be zero. And I have noticed a typo here, a typographical error. I missed the t somewhere here. So I'll iron out these small typographical errors before I upload it. Okay. So there must be a t here also. Okay. Now the question is, suppose Vx and Vy are zero. Okay. Then streamlines might intersect because the tangent is not defined. So consider a two-dimensional flow field. Okay. So you have the velocity vector having two components, Vx and Vy, and the Vz component is identically zero. So as we have seen, the equation of the streamline is dy dx equal to Vy by Vx. If you can solve this equation, you will get y as a function of x. That will be the equation of the streamline. Now, if both Vx and Vy are zero, then the right-hand side of this equation is of the form 0 by 0. So it is an indeterminate form. So you can try to find the limit of Vy by Vx. To be more precise, Vy, which is a function of x, y, and t, divided by Vx, which is another function of x, y, and t, as x and y approach xs and yx. But you can approach that point in the plane from different directions. And this limit might depend on the path by which the stagnation point is approached. Okay. So sometimes, in many cases, two values of this limit might exist. So how would you find these limits? Well, you can expand Vx and Vy in a Taylor series expansion about xs, ys. Or you can use the L'Hopital rule. And you may find that there are two finite values of the limit, okay, depending on how you are approaching this point. So in that case, two streamlines may intersect at the stagnation point. Is it clear?
Sir, but here, could we claim that the streamlines will end on that stagnation point?
Pardon?
Like, could we claim that the streamlines will end at that stagnation point? That is, they can't continue after that. After that, it would be some other streamline. So it would be like many streamlines coming to a point.
Find that two streamlines intersect at a point. Then the velocity vector there must be zero. Otherwise, there will be two tangents.
And if two streamlines are intersecting like at this stagnation point,
yeah,
those streamlines cannot extend beyond that, right?
Streamlines cannot intersect if the velocity is non-zero.
Yeah, that is true. But suppose that we have a stagnation point and a streamline is coming to, and two streamlines are coming towards that stagnation point. Then my question is that can they extend beyond that stagnation point? Beyond that stagnation point, those streamlines are different, right?
Yeah, so what I'm trying to say is that, see, I asked you this question, can two streamlines intersect at the point? Okay. And
Yes,
the immediate answer was they cannot, because then there'll be two tangents. Right?
Yes, sir. Yes, sir. Yes, sir.
Now, but the tangents are undefined if the velocity vector is zero.
Yes, sir.
you can define a tangent to the velocity vector only if it is non-zero. That is, the magnitude is non-zero. Okay. So when the magnitude of the velocity is zero, of course, not all points will be stagnation points. Okay.
Yes, sir.
For example, if you look at viscous flow along a solid plate, you can argue that velocity is zero at all points. Okay. But streamlines are not intersecting. Okay. So those are not stagnation points. Okay. So the concept of stagnation point is best understood in the context of inviscid flows. Okay. So imagine that the fluid is an ideal fluid. Okay. If it's an ideal fluid, it will slip along the wall. So then all components of velocity will not be zero over there. Okay.
All components of velocity would be zero there, right? No, will not be zero. Correct. Only one component, say Z component or something, will be zero. Yes, sir.
Even if one component of velocity is not zero, you can define the tangent.
Yes, sir.
In that case, two streamlines cannot intersect. Okay.
Yes.
So what I'm trying to say is two streamlines, if they intersect, that is possible only if the velocity vector is zero.
Yes, sir.
Okay. Now, I can give you an analog. You must have studied, done experiments on magnetism in the physics lab, either here in IIT or maybe in your school days. So have you drawn magnetic lines of force using a compass and a drawing sheet and a magnet?
Yes, sir.
Yes,
All
sir.
right. So you know the concept of neutral point in a magnetic field. So the magnetic line of force is something which is similar to a streamline. So the magnetic line of force is a curve in space which is everywhere tangent to the magnetic force at that point. So you place a compass, small compass with a small needle. All right. So the north pole and south pole of the compass will align in a direction which is tangent to that curve. Okay. Now, if you put 2-3 magnets nearby, okay,
Yes.
there will be several north poles and south poles, and it may so happen that there may be a point where the magnetic lines of force are intersecting. That is what you call a neutral point. But at that point, the magnetic force is zero because of cancellation effects.
Yes, sure.
So a stagnation point is analogous to a neutral point in a magnetic field.
Yes, sir.
So to be more precise, I would define a stagnation point as a point where streamlines intersect. Because when streamlines intersect, all the velocity components must be zero. Otherwise, they cannot intersect.
Yes, sir.
Okay.
Yes, sir.
But you could have points where the velocity components are zero, but it is not a stagnation point because there is no intersection of streamlines.
Yes, sir. Yes.
So this is a very important concept, and in this course you'll find that we will not be solving partial differential equations. Unlike other courses on fluid mechanics, we'll be using simple models which are one-dimensional, but if you want to understand how those mathematical formula are coming up, okay, then these concepts become very important. So to identify a stagnation point, you have to see if streamlines are intersecting. And if it's an inviscid flow, if you look at the neighborhood of the stagnation point, where would the maximum pressure occur? What do you think? If you apply Bernoulli's equation, that pressure plus kinetic energy, maximum pressure will be at the stagnation point. Because the sum of pressure, kinetic energy, and potential energy is conserved. So if you are in the vicinity of a point, the change in potential energy is negligible. Okay. So the point where the kinetic energy is minimum will have maximum pressure because the sum is constant. So a stagnation point will locally have the largest pressure. So if you're measuring pressures as an engineer at different points along a solid surface, let us say, okay, if you find a point where the pressure is maximum, it's possible that another streamline must have come from another direction and hit that solid wall at that point. All right. So what I'm trying to say is that you can have two tangents. That means two values of the slope. If there are two tangents, dy dx has two values, and that cannot happen if vx and vy are non-zero. But if both vx and vy are 0, it is of the form 0 by 0. So you can, of course, the limit might exist. So there may be a tangent, but the limit might be dependent on the path by which the stagnation point is approached. In which case, along two paths, you may have two tangents. And in fact, you can show that if the flow is irrotational, the angle between the two directions is 90 degrees. But in viscous flow, it may not be 90 degrees. Okay. Now let us look at steady flow versus unsteady flow. We'll be using Bernoulli's equation in this course. But as I said yesterday, Bernoulli's equation is valid only when the flow is steady. But sometimes you may have a case where the flow is steady in a translating frame of reference, but unsteady in a stationary frame of reference. So you have to figure out whether the flow is steady or not before you apply Bernoulli's equation. Now, how would you do that? Well, if you know the velocity field, you can see whether it varies with time. But another geometric way is to look at the streamline pattern. Now, the equation of the streamline I've written down here again. I've written it in my first slide, but here I've written the x, y, z, and t, the functions here. So as you can see that if the velocity components depend on time, then if you integrate this equation to find the equation of the streamline, you will have the equation of the streamline will have some time dependence. That means the streamline pattern will change with time if the flow is unsteady. So you might do a flow visualization experiment in the lab, and you can take photographs of the streamline pattern at different instants of time. If you find that the pattern is changing with time, that means the flow is unsteady. So this is a physical way of figuring out whether the flow is unsteady. Now suppose the flow is steady, then I'll write the same equation here, but I will not write the time dependence in the velocity components. Okay. Neither of the three velocity components depend on time, and therefore the magnitude v is also independent of time. So if I integrate this equation, you'll get a curve which is fixed in space. There will be no time dependence. It will not move with time. So in steady flow, the streamline pattern is fixed in space. So these concepts you can use to figure out whether the flow is steady or unsteady. So we'll come back later on to the Pelton turbine, and there you'll see that when the bucket is translating, with reference to the translating frame of reference, the streamline pattern will be fixed in space. But if you have an observer on the ground, you'll see the streamline pattern moving or translating in space. So the observer on the ground will see a flow which is unsteady. But an observer attached to the translating frame will see a flow which is steady. So we'll see that you can apply Bernoulli's equation in the translating frame, but that velocity which you use v squared, that has to be the relative velocity. So these are important concepts. So that is why I'm reviewing all this. Okay, now let us look at the term which is referred to as stream surface. So this is a surface which consists of streamlines. Now, as you know, velocity vectors are tangent to the streamlines. So the component of velocity normal to a streamline is 0. So no fluid can cross a stream surface. So if we look at the volume flow rate crossing any part of the stream surface, no matter where you are on the stream surface, the volume flow rate will be 0. If the surface is not a stream surface, you could have fluid crossing from one side to the other and on some part, and in the opposite direction on other parts. So there may be a positive volume flow rate and a negative volume flow rate, and the net might be 0. But here, if it's a stream surface, you can take any portion of the stream surface and there'll be no fluid crossing the stream surface. So the volume flow rate will be 0. Now, if you have an impermeable solid surface, you know that it is a stream surface. Why? Because if it's impermeable, the fluid cannot seep through. Now, if you have a porous surface with holes, maybe small holes, okay, then fluid can cross the surface from one side of the surface to the other. You may also have a membrane which is permeable, which will allow the fluid to go through. Then in that case, the porous solid surface will not be a stream surface. And the permeable membrane will also not be a stream surface. But if you have a membrane which is impermeable, then no fluid can cross that membrane. And you can identify it as a stream surface. So these are important. You must know how to identify stream surfaces because you may need to apply Bernoulli's equation along stream surfaces.
Sir, I have a doubt.
Yeah.
Sir, let us take any surface.
Yeah.
So on that surface, like the volume flow rate through any part is 0.
Yeah.
No matter what we take. Can we claim that that surface is a stream surface?
Right.
We can claim that. Hello?
Yeah. So any solid surface, if you take any line on a solid surface which is impermeable, it will be a streamline.
That is true because the velocity is parallel to the surface. But like I am saying, like in general, inside any fluid, like let us take a surface in which like if we take any part of it, the volume flow rate is 0.
Yeah.
Then can we claim that that surface is a stream surface?
Yes, it's a stream surface.
We can prove that.
Yeah.
Yes.
You know it's a stream surface. So if you find a flow field and a surface in the flow field such that along any point, so you take an infinitesimal area around any point on the surface. Okay.
Okay, so we can prove that it's tangent, yeah.
The volume flow rate crossing that infinitesimal area, if it is 0, then it's a stream surface.
Yes, sir.
So why I am emphasizing all this is that by looking at a sketch, okay, and making idealizations, you should be able to identify stream surfaces and stream lines and see whether it's moving or not. Okay, to figure out whether the flow is steady or not steady. Okay, so sometimes the physical feeling is also important, particularly in a course like this where you're not solving differential equations.
Yes, sir.
So that's why I'm reviewing all these concepts. Okay, now there's another term which you might have read before. It is called stream tube. So this is nothing but a collection or bundle of neighboring streamlines which are passing through a small closed curve, and they form an imaginary passage or conduit through which fluid flows. And the cross-sectional area of this conduit may not be constant, so it may be kind of a wavy surface, okay, undulating surface. So the surface of a stream tube will have 3 parts: an inlet section through which fluid will enter the stream tube, an outlet section through which fluid will leave the stream tube, and a curved lateral surface connecting the 2 ends. So stream tubes, stream surfaces, stream lines, these are all imaginary lines. It's not a tube with a solid wall or anything like that. So imagine that you have a conduit through which fluid enters and fluid leaves. Okay, so we are referring to the inlet section as section 1 and the outlet section as section 2. And the lateral surface is a stream surface, so no fluid will cross it. Now, if the flow is steady, the stream tube will be fixed in space. And if the flow is unsteady, then the stream tube will move. Now, are you able to hear me?
Yes, sir.
Yes, sir.
There is a power cut here, so I thought there may be some problems. Okay. So I'll continue for a short while. If the power cut persists, I may have to shut down and then restart again. Okay. All right. Let us look at what is a stream filament. So if you have a stream tube with a cross section which is very small, so small that you can neglect the variation of velocity over it, then you can call it a stream filament. So you can think of a stream filament as a stream tube with infinitesimally small cross section. So it's a collection of streamlines. Okay. Now I'll close this document and I'll go back to the first law of thermodynamics, which we discussed last time, and talk about it in the context of stream tubes and stream filaments. Okay, so I've opened the document which I was discussing last time, and here we were applying global.
Sir, you need to reshare the document.
Oh, okay, okay. Sorry. Thank you. Okay. So let us look at the what I was calling the global balance of total energy, or the first law of thermodynamics as applied to an open system or control volume. Now, I had written it in this form with one inlet and one outlet. So I'll emphasize again that m dot is the magnitude of the mass product. So we are always assuming it to be a positive number. And this is the energy that is flowing into the control volume. It is converted by the mass through the inlet. And the second term is the heat which is transferred into the control volume. So this law is applied to the system which occupies the control volume at time t. So on the right hand side, you have the flux of energy which is going out. It is converted out through section 2. And you have a term which involves shaft work. So between 1 and 2, if you have a shaft which rotates, okay, then you can either extract work from the fluid or add work to the, or add energy to the fluid. Okay. Now we can apply this. You can take the control volume to be a stream tube. In that case, this Q dot in will be the heat transfer between the fluid which is inside the stream tube and the surrounding fluid which is outside the stream tube. So if Q dot in is positive, then heat will flow from the surrounding tube, the fluid surrounding the stream tube, into the fluid which is inside the stream tube. And if it's negative, then the energy will be in the form of heat will be flowing from the fluid which is inside the stream tube to the surrounding fluid. Now this equation we rewrote in terms of the internal energy and the flow work PV. Okay, so I'll just refresh your memory. We expressed it in the form where you had kept the shaft work per unit mass for it on the left hand side. So if you look at equation 3, the left hand side is the rate at which shaft work is done divided by the mass for it. And the right hand side had P1 minus P2 by rho. So this is the contribution to the work because of the reduction in the pressure from inlet to outlet. And the second term is the contribution to the work due to the decrease in the kinetic energy of the fluid. So when the pressure and the kinetic energy of the fluid decrease, you extract work from the fluid. And if you're adding some work to it, then these terms will be negative. So the pressure might increase and the kinetic energy might increase. The third term is the change in the gravitational potential energy. That is usually negligible. And you have this term over here, which is E1 minus E2 plus Q dot in by M dot. So what I'm trying to emphasize is, if 1 and 2 are the inlet and outlet of a stream tube, then this Q dot in here is the heat that is coming into the fluid inside the stream tube from the surrounding fluid. And if Q dot in is negative, then heat is energy in the form of heat is being transferred from the fluid which is inside the stream tube to the surrounding fluid. It need not be a solid wall. So if you go down over here and look at this head loss term, this head loss we have defined as 1 upon G times E2 minus E1 minus Q dot in by M dot. And I want to emphasize that G is there just to get the terms on the right hand side in units of length or meters if you're using SI units. So you see that the head loss here is E2 minus E1, which is the increase in the entropy as the fluid moves from the inlet to the outlet. Sorry, increase in internal energy, specific internal energy. And minus Q dot in will represent the heat that is transferred from the fluid inside the filament to the fluid which is outside. So you can apply this to a stream tube or a stream filament. So minus Q dot in is the heat which is flowing out, because plus Q dot in is the heat which is flowing in. Okay, and this heat transfer is from one part of the fluid to another part of the fluid. So by using the concept of streamline and stream tube and stream function, okay, then you can explain this energy conversion process.
Sir, I have a doubt.
Yeah.
Stream surfaces can intersect, right?
Pardon?
Stream surfaces can intersect, right?
Stream surfaces?
Yes. They could intersect along a common streamline, I guess.
Yeah, it could. Suppose you have a flow field and there are two solid surfaces which are intersecting. Okay.
Yes, sir.
Then two stream surfaces are intersecting. That's possible.
What, like?
Because a solid
okay,
surface,
yeah.
which if it's impermeable, if both are impermeable.
Exactly. Like a T-bend or something. Yes, sir.
Yeah. But if you don't have solid surfaces, then only streamlines will intersect. Okay. Usually, all the neighboring streamlines may not intersect.
Stream surfaces. Streamlines can never
So,
intersect. Right?
If you don't have solid surfaces, okay, if you have a region of fluid where you have no solid surfaces, then only curves can intersect. Tubes will not intersect. Okay. So suppose you have a fluid which is at rest, then the velocity at each and every point is 0. You can't call them stagnation points. It's a static fluid. Okay.
Yes, sir.
So we are talking about special points in a flowing fluid. Okay. So in the flow field of a moving fluid, you may have certain points where the velocity vector is 0 and streamlines may be crossing. Okay. So if you have a flow field where you see streamlines are intersecting, two curves intersecting at a point, that point must be a stagnation point where all the components of velocity are 0. Otherwise, they cannot intersect.
Yes, sir.
And unfortunately, there are so many books in the market and also in our library, and you may have even books written by authors in well-known universities. Okay. I've seen statements made by authors saying that streamlines cannot intersect. Okay. There's a very good book by Fay. He's a professor at MIT. But if you look at his introductory chapter, he has made this error. He has said that streamlines cannot intersect. So he has not thought about stagnation points. Okay. Yes. Now, this being a second level course, I think I would like to emphasize these points. Okay. And these might help you in solving problems. So if you want to find the location of maximum pressure and you're modeling the flow as an inelastic flow, ideal fluid flow, okay, then look at points where streamlines are intersecting. And at the stagnation point, locally, your pressure will be maximum. Okay. So if you are very strong in this fundamental concepts, then you'll be able to solve the problems very easily.
So associated with that, there's one more doubt arising also. Like
Yeah.
streamlines intersect at the stagnation points, right? Then for an inviscid flow, the Bernoulli function should be the same along those streamlines, right?
Yeah, but if you move from one streamline to the next, the Bernoulli function might change. If the flow is rotational, that is, the vorticity is non-zero.
Despite of them be intersecting at a stagnation point.
Oh, you're talking about a case where they're intersecting.
Yeah, so then to Bernoulli function.
If they're intersecting, then the Bernoulli function will be the same.
Yes, sir.
Because one point is common to them.
Yes, sir. Yes, sir.
Yeah. If they're intersecting, then the Bernoulli function will have the same value on both the streamlines, provided the other conditions are satisfied. That is, the flow is steady, density is constant, the force field is conservative. Okay.
Yes, sir. Rotational won't matter there, right?
Pardon?
Rotational or irrotational flow won't matter there, right?
No.
Ah, yes.
See okay, let me go back over here. Okay. That is in another document. So I'll stop sharing this and open that one.
Sir, before that,
okay.
Sir, why are we consider stagnation point? Because in theory also, any particle cannot reach that stagnation point. Means no particle can go there, because before going there only the velocity starts to go to zero. So we can neglect that and still be theoretically rigorous, right?
Can you say that again?
Means no particle will be able to reach the stagnation point, as before going there only the velocity will become zero. So it will reach there after an infinite amount of time.
Right. So it is a singular point actually.
Yes, sir. So we can
neglect that point, and the particle which is at that point will not move at all. Okay. So in your second year course, you might have solved problems where you found the path line of a particle. Okay. So I've taught that course several times, and I used to give problems where I used to ask students to find the path line at a point where the velocity is zero. And that's a degenerate case. There's no line. It is just a point. Okay. So the fluid particle which is at the stagnation point will not move at all. Okay. And the neighboring particles then move very, very, very slowly as it approaches the streamline. As it approaches the stagnation point, its velocity will keep on increasing, so it will take infinite time to reach. That means it will never reach. Okay. So this is one of the problems with the continuum description of the fluid flow. Okay. So you have to keep in mind the fact that when we talk about a fluid particle, it is not a physical entity like a molecule or atom. It is just a imaginary concept in the continuum model. You are simply postulating that matter is made, the distribution of matter is continuous, and you have an infinite number of particles. Each point is a particle. Okay. So a stagnation point actually then is a singular point in this continuum description. Okay.
So does that mean that mass will keep on accumulating at the stagnation point?
No, mass will not accumulate because that particle there will not move. So when you talk about mass flow rate, you have to consider an area around that point and see if mass is crossing that area. Okay. So if you take, if you have a stagnation point which lies on a solid surface, which is impermeable, and you take a area element along the solid surface, then what you say is true. There will no fluid will cross it. But suppose inside a flow field you have a stagnation point. Okay. And you consider a small area through the stagnation point, then what will happen? At the stagnation point, velocity will be zero, but if you move slightly away from the stagnation point, the velocity is not zero. So fluid will cross. Okay. So a point has zero area, so you cannot talk about fluid crossing a point. You can only talk about fluid crossing a area, which is might be infinitesimal, but still it's an area. It will have more than one point.
Yes, sir.
Sir,
Yeah.
Regarding the, can't we say that instead of saying that they do not intersect, can't we see them as magnetic lines of force where they seem to go towards a point of intersection, but somehow they're repelled and they follow a different trajectory. I mean, they're bent sort of. So they actually don't get a chance to reach that point instead of thinking like they can intersect or
Yeah. So if you have a stagnation point inside a flow field, the particle which is sitting at the stagnation point, it will not move at all. Okay. And along the two streamlines, particles will approach it. But it will approach it in such a way that it will never reach it. It will take infinite time to reach it. So that is why I said this is a singularity in the mathematical model. But it's only one point, so it